We're given f of x comma y equals natural log of the quantity x squared plus y squared, and asked to determine the directional derivative of f in the direction of the vector with components -2, 2, and at the point 1, 3. Again, let's first look at this graphically. Again, our goal is to find the value of the directional derivative at the point 3, 1, which would be the point here in the xy plane. The second point up here on the surface would be the corresponding point where to find the z-coordinate of this point. We'd have to substitute the x and y values from this point into our function f of x comma y. And then from this point, we want to find the slope of the tangent line in the direction of this red vector, which is the given vector with components -2, 2. So again, the slope of this blue tangent line from this point in the direction of this red vector would be the value of the directional derivative that we're looking for. Let's go ahead and rotate this so we can see this from different angles. Also notice how I included the plane that includes the directional vector to add better perspective. Going back to our work, we know from our previous examples, this is how we're going to find the value of the directional derivative. So we'll have to find the partial derivatives of f and then evaluate those partial derivatives at the point 1, 3. And then to find cosine theta and sine theta, we'll find the unit vector in the direction of our directional vector with components -2, 2. So starting with the given function, we'll first find the partial derivatives. Let's first find the partial derivative with respect to x. So we'll differentiate the given function with respect to x, treating y as a constant. Remember, the derivative of natural log u with respect to x would be equal to 1 over u times u prime, or 1 over u times du dx. So the derivative of natural log of the quantity x squared plus y squared with respect to x would be 1 over the quantity x squared plus y squared times the derivative of x squared plus y squared with respect to x, which would just be 2x. Remember, the derivative of y squared would be 0 with respect to x because we're treating y as a constant. So this would just be 2x divided by the quantity x squared plus y squared. And now we need to evaluate this at the point 3, 1. So we would have 2 times x, which is 3. And notice how the denominator is going to be x squared plus y squared, which would be 3 squared plus 1 squared, which equals 10. So the partial derivative with respect to x at the point 3, 1 would be equal to 6/10, which simplifies to 3/5. And now we'll find the partial derivative with respect to y. So now we're treating x as a constant and differentiating with respect to y. So the derivative of natural log of the quantity x squared plus y squared with respect to y would be 1 over the quantity x squared plus y squared times the derivative of x squared plus y squared with respect to y, which would be 2y. Again, the derivative of x squared with respect to y would be 0 because we're treating x as a constant. So here we have 2y divided by the quantity x squared plus y squared, which we now need to evaluate, again at the point 3, 1. So here we'd have 2 times y, which is 1, all divided by, again, 3 squared plus 1 squared. So here we have 2/10. So the partial derivative with respect to y at the point 3, 1 is equal to 2/10, which equals 1/5. So we need this value and this value to find the directional derivative at the given point in the given direction, but we also need to find cosine theta and sine theta by determining the unit vector in the direction of the vector with components -2, 2. And let's do this on the next slide. The unit vector is going to be equal to, if we let this vector be vector v, we'd have vector v divided by the magnitude of vector v. So vector v has components -2, 2. We'll divide by the magnitude, which would be equal to the square root of -2 squared plus 2 squared. So we have the given vector divided by, this is going to be equal to the square root of 4 plus 4, the square root of 8. Because 8 is equal to 4 times 2, The square root of 8 simplifies to 2 square root 2. So let's write this as negative 2 divided by 2 square root 2, comma, 2 divided by 2 square root 2. So the unit vector in the same direction as the given directional vector would have an x component of negative 1 divided by square root 2 and a y component of 1 divided by square root 2. So now we know that cosine theta is equal to negative 1 divided by square root 2, and we know sine theta is equal to 1 divided by square root 2. And now we have all the information we need in order to find the value of the directional derivative. The value of the directional derivative at the point 3, 1 in the direction of the vector with components negative 2, 2 is going to be equal to the partial derivative with respect to f at the point, which is equal to 3/5, times cosine theta, which equals negative 1 divided by square root 2, plus the partial derivative of f with respect to y evaluated at the point, which is 1/5, times sine theta, which equals 1 divided by square root 2. So here we have negative 3 divided by 5 square root 2 plus 1 divided by 5 square root 2. So notice how we have the exact value of negative 2 divided by 5 square root 2. Let's also get our decimal approximation. So we have negative 2 divided by, and then in parentheses, we have 5 square root 2, right arrow, close parenthesis, and enter. So notice how the directional derivative is approximately equal to negative 0.2828. Now let's go back to our graph and take a look at this again. Notice how if we're on this point on the surface and we move in the direction of this red vector, notice how the line is slanted down in this direction, and that's the reason why the directional derivative in this case is negative. I hope you found this example helpful.